Hi, welcome to our Hyde lecture series, the first one of the spring semester. I'm very excited to introduce Bradley Cantrell. Brad, thank you for coming to Nebraska. We're happy to host. Brad is a landscape architect and scholar whose work focuses on the role of computation in media and environmental and ecological design. Professor Cantrell received his Bachelor's of Science in Landscape Architecture from the University of Kentucky and his Master's in Landscape Architecture from the Harvard Graduate School of Design. He's held academic appointments at the GSD, the Rhode Island School of Design, Louisiana State University, where he was the Robert Wright School of Landscape Architecture Graduate Coordinator and Director. His work in Louisiana over the past decade points to a series of methodologies that develop modes and modeling, simulation, and embedded computation that expresses and engages the complexity of overlapping physical, cultural, and ecological systems. Cantrell's research and teaching focuses on digital film simulation and modeling techniques to represent landscape, form, process, and phenomenology. His work in digital representation ranges from improving the workflow of digital media in the design process to providing a methodology for deconstructing landscape through composition and film editing. Brad is the author and co-author of several books. One that all landscape architecture students know very well is the Digital Drawing for Landscape Architecture, which won the 2012 ASLA Award of Excellence. It's also being printed in its second edition. Second book, Modeling the Environment, which explores an approach to digital modeling that's specific to environmental design. And his most recent book, Responsive Landscapes, which highlights a range of case studies in architecture, landscape architecture, computer science, and art that employ responsive technologies as a mediator of landscape processes, which I believe will be the basis for his talk today. So I'd love to welcome Brad, and we look forward to your lecture.
Thank you for the introduction, Sarah, and thank you for the invitation to come and lecture. I'm honored to be here and honored to kick off what looks like a really exciting set of lectures for the spring and on. You guys really have an amazing group, and it's great to be part of it. So my work, and just to give you a little other background on me, my background in both of my degrees are in landscape architecture. But before that, I started in a really long undergraduate career where I started in paint as a painter, and realized that's not what I wanted to be, and kind of overcorrected into computer science, and did that for many years, and realized that's not where I wanted to go. And then basically did manual labor for a little while, and realized someone pointed me to landscape architecture. So I was planting trees and realizing that maybe that was some sort of medium. And so landscape for me was never one of those things that I kind of was born into and thinking that this is what I was going to do down the road. But it's certainly something that I found pulled together a whole series of interests. And you'll probably see that in some of my work. So one of the things that Sarah mentioned is a lot of my writing has been on how we represent landscapes or environments, and then particularly how those tools, those digital tools, are basically evolved from a series of analog tools, and those analog tools, in many ways, we are just re-simulating using the computer. So it's not necessarily that we've kind of reappropriated computation for anything other than re-simulating a set of analog tools. And this is this kind of Lev Manovich quotes gets at this, but it speaks to the idea that there is no real digital media. There is no kind of real concept of that. What we kind of think of as digital media is a simulation of a whole other set of analog mediums. And part of what I'll point to is possibly ways that I believe through these ideas of responsive technologies that we're actually getting to a point where computation is part of our physical world. So a couple things to kind of put up front there, and one of them is that there's a couple benchmarks that I would lay out there that I think are important for all of us to either agree on or disagree on, but that are based around the way I view landscape. The first one is that I would put out there that the world around us is this kind of synthetic construct. It's this thing that we've made, we've constructed it, and we're kind of constantly in interaction with all of these landscape systems. There is no kind of benchmark or baseline for some version of nature that is beyond the one that we're kind of actively involved with. And for me, that's an important way to view the world. Not to say that we can do whatever we want, but to say that we are actors in that world, not remediators. I think this kind of comes up in many ways, but one of the ways that this becomes extremely apparent is when you start to look at watersheds like the Mississippi River Basin or others. It's very easy to take the Mississippi River and make the argument that this river system is basically a hydrological watershed that has been constructed by human beings 100%. It's no longer under the influence of natural systems, and in reality, the kind of evolved systems are in combination with a series of kind of maintenance regimes that we're using to constantly bind this river into its current form. And that happens, through the kind of infrastructure we build, and it happens, as I mentioned, through forms of maintenance. I'll go past this really quick because I just mentioned it, about our influence. But you can see this in this slide here. Something like the Mississippi River, which at one point actually flooded this whole deltaic plain, has been channeled in ways that it's basically dumping all of the sediment from the Midwest out into the Gulf. And so what it would be the shortest route, what you're seeing on the left, where we're getting some sediment, has been this longer route past New Orleans is being maintained, and we're dumping sediment out there. So we're not nourishing this delta anymore. And this kind of human influence is through a whole range of things, through the dredge operations I mentioned before, but also through huge infrastructural projects. Infrastructural projects that span huge parts of the landscape and control it in what you can imagine as very articulated ways. Particularly something like the Morganza spillway here, which can basically holds the Mississippi River back, but can release just the amount of water they need in order to maintain the larger systems, the water levels. So all of these systems have been put in place for really a couple purposes. One, to protect human settlement, and the second has been to create easy navigation on the Mississippi River. And with those two kind of goals in mind, we've built this watershed. And so I say that about the Mississippi River, but I think we can look at nearly any river system, we can look at nearly any coast, and we can understand it in that way. There's not necessarily a good or bad that I'm adding to that label. All I'm putting out there is that we have to take a kind of we'd be very conscious that we are affecting the world in these very large ways, and something like the continental U.S., 60% of it is under our control when we think of the Mississippi River watershed. And control is a loose word, but we're altering it. The other aspect that I think is important just to throw out there is that there's a whole series of ways that we're seeing the world that we've never actually seen it before. And this is nothing new, but we take it for granted today about the way we consume the processes of the world around us, and particularly landscape phenomena. We think of someone like Edward Muybridge's work and his revealing of the gait of the horse basically by setting up 12 cameras, taking a frame as the horse ran by, but revealing the fact that the horses, all four horses' feet come off the ground during its stride. This revealed a new idea about the way the horse interfaces, or the way the horse runs. But many of these kind of landscape phenomena are being revealed every day through the way we're sensing the environment, the way we're imaging it, the way we're reprocessing those images. We can think of this in kind of multitudes of ways. This is just using split scan photography to look at waves. And in this sense, we're using rapatronic photography to take a picture of a nuclear bomb the moment it explodes. or even kind of long exposure photography. But there's a whole range of other versions of this, and it's not worth kind of going into, but we understand that things like Google Earth and aerial photography and these mapping tools, as well as these kind of visceral visual tools have changed kind of our sensory palette, or augmented our sensory palette. And then the other one I would say here is that a series of tools that are deployed quite heavily in architecture and are being deployed in landscape, that are being used to build models of systems and simulations of systems. And those simulations are often being calibrated to real-world phenomena, but also become their own place. They become their own version of the world that we begin to use and we act upon. So some of the kind of methods and techniques for this come through forms of visualization then and simulation as ways of unveiling kind of overlaps between disciplines, but the ways landscapes work. But a lot of the way I've explored this over the past, say, decade has been through forms of visualization. And many of these are things we've probably seen. This is part of a longer animation we did at Louisiana State University. But visualizations and animations like this that begin to tie together geological processes with kind of shorter term issues of settlement and infrastructure on the delta. So this ties it back into the way the land was built by the river system. And you can see here kind of the timeline above, and it's kind of the way it plays out on the land. Or even animations that begin to explore how these kind of sediment systems might begin to build land or change ecological systems. And I'm showing these just to show kind of the character of some of these visualizations. And then others that we tried to develop that also took the kind of best science we had at the moment about how the river was working and tied that back to the kind of everyday operation of the river system. And so in this case, looking at one of these, what's called a sediment diversion on the Mississippi River, but looking at kind of how it would behave through historical data, but then also tying that to the way the river system might work. And so this animation begins to do that, but while also trying to pull together some of the character of this landscape. So it's not just about the operation, but also the feeling of what that place is about, and the way it might operate. Dry mouth, have a Marco Rubio moment here. These animations, though, I think are important for us as landscape architects to tie together, this information that's in scientific papers, the kind of recorded information from site, and pull together the way that those systems might work. What's also important then is how we go from these kind of presentations and begin to build models that we can interact with and begin to evolve. And I use a precedent that I'm always interested in, the Mississippi Basin model, which we'll look at, but these two quotes here, one of them that I think is important, and that's Bolding's quote, and it's the one that I always go back to, which is this kind of cynic's quote of, a system is a big black box of which we can't unlock the locks, and all we can find out about is what goes in and what comes out. And I would, with many of these tools, I think a lot of us are trying to peel back that black box and get into kind of how we build these models. But I think it's important to always realize that there is this kind of obfuscation that's always going on with these models, and that there's these kind of pieces that are, they're not completely virtualizing these complex landscapes, but they become their own landscapes unto themselves. And I think a great example of that is the Mississippi Basin model. The Mississippi Basin model, if you're not familiar with it, is in Clinton, Mississippi. It's on a 200-acre site and was built in the late 1940s, early 1950s, and ran. They basically used this model for about 50 years, up into the 90s. with the basin model, you basically have 20 acres, and you can kind of see this on the interior. So if you see that kind of concrete area on the interior, you have about 20 acres that are kind of precisely modeled, and it's the watershed itself. And so I'm going to go forward a couple slides and show you this. But this is the kind of model extents. And so the red area is the area modeled in concrete, and then the white area is the larger 200-acre watershed. It's currently kind of falling apart. It's in pieces. It's actually kind of surreal because when you're out there, there's a model airplane track, and there's drones flying around, and there's also model RC car track. So you have these kind of weird relationships with that. But the model was built kind of for multiple reasons. One, it happened to be built at a time whenever modeling itself was thought of as a imprecise way of understanding the world. And in many ways, the numerical models they were building weren't that precise yet. But it was during a time when field study was where all of the information geologists and geomorphologists were gathering about the world. The basin model went through a few smaller iterations to prove that it could actually work. And it was then built here in Clinton, Mississippi. And what you can see here is that not only was it used as a way to understand the way the river worked, but it was also used as a way to promote or market changes to the river system. It was, as I mentioned, modeled all in concrete, and it was a performative model and this kind of tangible and visual model. So you can see in this kind of picture on the right here that not only do we have this concrete channel with gravel that's working to slow down or speed up the water, but we also have these kind of simulated vegetation with wire. The model also was one of the first times that anyone really saw the whole Mississippi River watershed as one system, so as one piece. And so it gave us this kind of instant overview of the river. Built by the Army Corps of Engineers, you can kind of see the early days of it here with the grading and the concrete channels. Another version of that, and here you can see a couple things. One of them is the wire mesh that is basically simulating the trees for friction coefficient. But if you look on the edges of the channel, you also see the scoring that went into that, which basically is slowing down the water and simulating like riverine vegetation. Now the river. The model was also in the late 40s, early 50s, completely automated. So for the time, there was a series of valves and pumps that they could open and close at the different tributaries that would basically allow them to run different scenarios. And so they would take historical data about the way the river performed. They would run it through this automated system, which were basically big spools of paper that had if you know what punch cards are, they had the punch card holes in them, and they would turn off and on the valves for specific amounts of time in order to simulate these major water events. And so the model was first basically conceived through mathematical or numerical models, but then tuned over time, particularly around kind of scalar issues, that to based on this historical data. So they basically would run the historical data. It wouldn't behave correctly. They would see where the things weren't behaving. They would adjust the model and then basically tune it to behave the way the river behaved through history. It actually, in 1952, predicted the exact kind of water levels right here near Omaha, Nebraska. And this is like its big moment. It actually worked. They were able to deploy the right amount of sandbags, deploy the right amount of levee protection, and it saved the day in that case. What it did beyond basically being like doing a simulation for storm prediction, it also created a whole range of justifications for different infrastructure, particularly levee infrastructure from St. Louis down to Baton Rouge, Louisiana. And many would make the argument that the model, well, and you can look at this, the way the model was built in the 1940s, the actual river course of the model in the 1940s, is the exact same river course that the river holds today. And this is an unusual fact about the Mississippi River. The Mississippi River is somewhat, for many years, a very active river, jumping its banks, finding new courses. But it's been basically, the river has taken on the model in some sense, and it's been held in its current locations. And this is kind of the current. Well, this was in 2006, but this is the model kind of in its current state, which is falling apart, but you get the idea here. These are some of the concrete panels. Now, so if you see here, these are some of the computer rooms where they would have the spools of punch cards to run the valves. So why I bring up the basin model is very much about this idea of understanding kind of a system in its totality, or being able to work with a system. Some of the shortcomings you can see of this immediately are the kind of minimization of variables within a very complex landscape. And so in this case, you're working really with one issue on the river, and that's water velocity. So you're really just working with the speed of water, speeding it up or slowing it down, kind of work to test its behaviors. And you're also working at it on very disparate scales from, this is a 1 to 1,000 model, but 1 to 100 in the vertical. So you get all kinds of weird issues between those two systems. But at the same time, there's enough kind of similarity that it can be predictive, and it can also be used to kind of imagine new ways or new types of river infrastructure. The other part is a lack of flexibility, and so that's obviously another kind of issue with this type of model. Today, there's not a lot of these physical models. I mean, I say that there's a large river center near Minneapolis, and Louisiana State University is dedicating a bit to physical modeling. But in general, many of these models are something like the Mississippi Basin model could very easily be simulated in your laptop. That same set of variables in terms of Manning coefficients could be simulated on your laptop and much faster than the time scale of that system would run. And I think to think about that, about what was happening in the 40s and the kind of massive amount of change that was happening in this landscape, to me that's a really interesting idea, that suddenly we can kind of have the turnover of 1/1000th of the amount of time, and we can process that in our laptops. The models are getting much more complex. They're getting much more kind of deep in the way they're working. But they're still not even coming close to approaching the complexity of how the river system works. The other, this shows a model at LSU that Clint Wilson, who's a professor there, has been working on. But this kind of combines two ends of things: one, the physical modeling, but also with an overlay of digital sensors. And so he's kind of embedded both of those into that, as well as forms of projection, which we're not seeing here. So in the design studio, our hope is to sometimes bring some of these ideas back into that. And so one version of that has been these kind of tabletop models we did at Louisiana State University that would use live vegetation, and using that live vegetation, using alfalfa, which grows very quick and dies off, we would use that as a way to hold the soil together, but then to simulate these kind of meandering streams. While they aren't there to represent any specific river, the idea here is to kind of take the science we're reading and then have a kind of this model on our tabletop that we can observe and then begin to build other types of models from. Faster here. This gets translated to other forms of representation. Past this. But also then beginning to take those physical systems and with digital simulation, trying to come up with methods of markup that would, in this case, speak to velocity, but that make them accessible to students. At the end of the day, though, with this kind of these forms of simulation, what we're really getting at is building the model that's intrinsic about a very small part of that system that we believe can kind of play out in a much more kind of intricately detailed organization. So what you're going to see as we kind of move forward is that idea of these kind of smaller models, these kind of smaller modes of sensing, that then begin to kind of aggregate into the way larger systems may work. The other aspect of this, and you know, Scott, once again, I'm taking kind of his cynics version of this, but his version of the kind of form of control is this idea that we're looking at the world then through these very selective realities. We start to build these versions of the world that become extremely selective, which is another aspect that I think that we'll touch on here in a moment. With these, with these simulations and these models, part of it is kind of design inspiration, but other parts are very much about testing, and particularly testing scenarios, not necessarily to find the optimal result, but to think of them as ways of generating new design ideas. So for some of the design studios we've been teaching, we've been using the kind of performance aspect, but then trying to generate new types of landform from those, particularly types of landforms that kind of play in between these kind of, like these edges in this case that are much more static, and this kind of middle ground that is much more fluid. Past a few of these, but some of these kind of tests that students are doing, I think, become somewhat interesting. And ones that we've probably all seen are these kind of tests on wind or fluids, in this case wind, but then using that as a way to generate types of landform that are attached to context. So the other aspect here is how do we begin to use simulation? So in this case, we're thinking of it as generating landform. How do we begin to imagine or prototype the tools for landscape architects that allow us to approach ideas about indeterminacy, ideas about succession, ideas about change over time, and I think there's you'll see some of the tools you've seen already do that. In this case, this was a student thesis project by Ben Wellington at Louisiana State University, and what he worked on was a successional model that allowed him to basically go in and put together a planting scheme, see how the successional model might play out, and even going forward in time, well, in this case, he's changing species, so the succession model changes, but going forward in time and painting basically the future version, and then using the successional model to kind of go back in time. Now, while I'll say that model is not extremely accurate, this idea of kind of jumping forward and backward through simulation is one that I find extremely interesting, and not necessarily to say we know what the future is going to look like, but certainly to use that as kind of this imaginative future state. Okay, so let me jump forward to this last concept before I get into some of the projects. So this idea of all of these kind of tools, particularly the ones around simulation, become, in my mind, extremely interesting whenever we begin to think of those tools embedded in the kind of landscape or biological systems themselves. And we've approached this in numerous ways, in many ways the same way architecture has. Many of the projects I've worked on over the last years have been very much about these kind of installation type projects, and so using the kind of technologies of motion tracking or sensing in very controlled environments, but then trying to begin to extrapolate from that ways that we might begin to use this in the landscape itself. And so, this is using kind of all of the basic tools of Arduino and other kind of prototyping microcontrollers, but really trying to get to the nuts and bolts of how we might sense landscape phenomena. In this case, these students were looking at saltwater concentration running across this bed, but how that might tie itself back into modeling software, and how that might actually begin to be used to sense very specific ecological processes as they occur. In this case, the students were looking at algae content in water, and developing ways of sensing that and responding to it by sequestering very specific moments that the algae was growing. Or other versions of this where students are looking at these buoys that actually follow the course of the changing river in order to enable navigation. Other tools we've looked at in the lab have also imagined that having these kind of abilities to change landscapes in real time or very quickly, not very quickly, but be able to make adjustments on smaller scales, that the process of building landform might be different than we imagine it now. The idea that that process might be less about moving dirt exactly where we want it, but more about deploying it in these very thin layers. And what kind of forms we might get from that, but then how that in section might actually build a much more complex strata for landscape. And I think some of these kind of terrain modifications really look at these kind of micro deployments and how that strata gets built. And then the last version of that is another set of tests that Justine Holtzman worked on in the lab. And these were very much about how soil and the chemical processes in soil might be altered to basically change it consistently between kind of a liquid or solid state. And that with that idea, you might be ossifying or liquefying soil strata, and as landscape processes started to work on that, you're either kind of speeding them up, or in a sense catalyzing them, or slowing them down by ossifying them. And her work tied kind of deeply into ceramics, which was where her field was, or where her background is, and so hers became these kind of what she called actant tests, and in ways looking at how you might even just change the color of the soil, but how by embedding other materials or catalyzing it, you might actually erode it quicker or solidify it. And so these became not only these kind of actant tests, but also these field tests in terms of how this might work across kind of a larger range of materials. So, and I'm going quickly through these, but what this tries to set up for us in the laboratory is other ways of imagining the way the landscape might function. So it's kind of rethinking some of the tools we use to construct the landscape, but also reimagining the way our inputs within the landscape would change. And there's kind of two versions of this that I think are pushing this boundary. One of them is at the Landscape Morphologies Lab at University of Southern California. Alexander Robinson has been doing quite a bit of work with basically with the KUKA robot and tool paths, but really about moving sand using these different tool paths and how this kind of movement of or these tool paths build these kind of different landforms. And these are all automated landforms he's making, but the really interesting part about this, part of it is the kind of automation of this system, which I think is interesting and kind of surreal to watch as it builds each of these models. But he's also then tied this system into a series of projections that actively analyze what's going on those surfaces. So looking at slope, looking at view and aspect, as well as tying that system back into a gaming engine that allows him to kind of occupy each of those models. So as they're being kind of constantly remodeled, you're actually kind of occupying those spaces. Or in this case, flooding them with certain amounts of water. So the interesting thing about this is, it's not only it's kind of pushing two things together. One is the process of visualizing, the other is the process of construction. And while there's nothing perfect about this in Alex's work, it starts to kind of pull those two pieces together. Another version that I would point to is the work we're doing at the Responsive Environments and Artifacts Lab, and that has to do with ways of using these sediment models and beginning to interfere or interact with the way the sediment is being deployed. And so what we're looking at is how we can take these sediment models, and so in this case we have these kind of hastily constructed versions of this, and I'll show you the one we have now, which is slightly nicer. But in this workshop, the students began to develop their own ways of interfering with the sediment flow and using very basic instruments to to slow down or speed up the water, but by doing that, they're able to either cut or build land. And so by choreographing that system, they're able to grow or cut away these landforms. Some of these kind of working here, and some of these are a little silly, like this giant crab these guys built. But in reality, what some of these are doing up here is they're actually kind of building and cutting away that surface. Now, in a slightly more precise way, we've also worked with kind of a larger view of the model using a connect to get basically a real-time model of that surface. And then developing this, basically what you could call a sediment diversion, similar to the Morganza spillway, that we can then operate the gates on that diversion. What we're able to do here, in a very basic way, is we're able to create new landforms very precisely near the gates and a little bit fuzzier farther down from the gates. And so basically with that, we have this kind of precision on the left, and we're able to then kind of choose how we want to dump the water or speed up or slow down the water as it moves down that set of gates. So by simply opening a gate or closing a gate, we can begin to alter that flow. And using that, we can I won't say precisely, but we can, within a pretty good margin of error, begin to print those kind of landforms farther downstream. You can see that in this time lapse. What I find interesting about this is this kind of overlap between two things. One, the behavior of the gate itself, the behavior of the sediment system, and those two interactions making this new system. And it's being done in a way that, or it's being done consciously in a way that is, right now I would say it's not necessarily producing land for any specific purpose. But there can be this kind of conscious choreography between those and this kind of reciprocal relationship as you read what's happening downriver and you're able to then reappropriate the way the gates open or close. So the version we're working with now is similar. We're hoping to take this a bit farther than it was in that last model, but we've worked with a company called EM River. And we've, with them, developed this sediment model. Within this, we have a couple ways of sensing the surface, and I can show you that. One of them is using ultrasonic sensors. Basically, that's giving us a distance, and we're able to move those ultrasonic sensors across and cut a section anywhere along the model in real time, and that's with very high precision. And then on the other end, we're able to use photogrammetry and also the connect to build a real-time model of the surface itself. We also have, and this is not so easy to see here, but you'll see in another one, a series of hoppers that hold the sediment that we can then program each of them to release the sediment as the water is flowing to the system in order to represent different sediment loads within the model. The model is also this kind of plastic artificial sediment that gives us a very kind of fine black sediment, which is very small and has a high specific or low specific gravity, and up to the yellow sediment, which is much bigger. But that model then we can run for very long periods of time, and similar to the models I talked about earlier, not really representing a specific river or specific delta, but becoming its own site that we can work within. So that as a site, we have this kind of ever-evolving landscape, and that landscape is once again kind of stripped of many of the variables that are in actual landscape systems, but gives us a way to begin to imagine new ways of interacting with that system. Basically using the entropy of the river again, as I mentioned before, as the power behind making new landforms. So this one is kind of a view of that same model running, but this is the image coming in from the depth sensor. So we're able to then query that model, and we can act upon that in many different ways. And then this next video here really just shows the So we have these, as I mentioned, these ultrasonic sensors that we're able to kind of pull back and forth across the table. And with that, we're able to, we're basically measuring the distance from the ultrasonic sensor to the surface and able to get a section of that surface in real time. So as a space to work in, this becomes interesting because the model then is live, it's performing, and we're not necessarily saying that this is the actions here pertain exactly to some other river, but that this other space, this other model space, is one that we can begin to imagine how we might work with these kind of micro adjustments in larger landscape systems. Some of the student work has not only looked at the way the model's functioning, but also then building these kind of smaller tests. And so these were using, he's using cymatics, so he's using vibration. But what you'll see here, if I can, he's also then working with these to build new visualizations. And so let me see if I can actually. So he's, with that, then trying to derive a language about how those systems are working. And these kind of lead to a series of active diagrams which build themselves up over what he's learning from each of these different vibration patterns. And then taking these kind of smaller tests and then placing those same ideas and forms of analysis back into modifications on the table and beginning to revisualize those. And so his project was just all about a series and methods of visualization. And then this other set of students used a very basic set of planes that they readjusted over time, but used that as a way to develop a new set of landforms. Basically developed almost as a palimpsest. So if you kind of see that here, what that sets up then is a design language all built around the kind of manipulation of that fin, right? But in reality, once again, not really understanding exactly what the landform is going to look like, but having this kind of range or fuzziness to the way that landform might be built. So, some of the things that we're working within are these tools to really allow us into this other what I would consider this other realm. It's in a way breaking down the door of the static model. It's also then giving us new ways of seeing the way that model performs. It does lead us to a whole set of ways then we can begin to take and appropriate the ways we're using technology to interact with the world and kind of and not even reconceive them, but adopt them in landscape architecture. And when we do that, as I mentioned, we're doing that through the kind of similar tools to the other arts and architecture. But what we're hoping to do is, reimagine this kind of single variable system that's all about speed of water and maintaining speed of water at very specific rates, and beginning to merge multiple variables into those systems. In some ways, going beyond this idea that we need to, we can only sample a few pieces, but that each of those samples actually ties back into a much more intricate system. I'm going to go past a couple slides here and just jump into some of the things we worked on in this book. So the Responsive Landscapes book has been a project I've worked on for the last 3 years. And really what we've done with that book is taken a whole set of architecture, art, and landscape case studies and began to somewhat categorize them, but also pull out from them the way we're seeing them work within landscape. And many of these pertain to architecture too, so I wouldn't wholly say they're only about landscape. And the book is broken down into these sections. One section that we call elucidate, which is really about projects and about a set of methodologies that are about revealing hidden systems. Another one that we call compress, which is very much about ways we are changing timescales of the way landscape phenomena works. Displace, which is moving a phenomena from one place to another typically. The idea of connecting, so connecting from virtual to physical or vice versa, or even just in the kind of wormhole sense, connecting locations across space and time. Philip Beasley's work, this idea of this kind of ambient or this kind of life form that, that technology can have or construction can have. And then finally, the last section is very much on this idea of modification. And even the chapter we wrote for this really looks at the projects we present there, which some of them are speculative, some are realized, but imagines this kind of process of modifying the landscape as partially about the construction itself, but the process being its own method of inquiry. The idea of changing, reevaluating, and changing again becomes its own form of analysis. And by doing, by doing is the only way we can actually start a project along these terms. So we have a little more time. The last kind of piece here is to kind of look at a couple projects or speculative projects from the lab, but also speak about a few more quick ideas. One of them is the idea that when we start to think about these responsive technologies, one of the things that I think becomes really important is that we think of humanity as an actor in a much broader set of actors, and in many ways decentralizing human beings from their own idea that they're modifying the world for themselves. And so you'll see some of the projects are somewhat about kind of making new place for people, but in many cases it's really about having slightly more intelligent interactions with the world around us that may benefit humans or just actually benefit the larger ecological system. So what this really means is kind of if we think of this cybernetics feedback loop of sensing and processing and acting on that or visualizing it or actuating it, what it takes that kind of single feedback loop or even the kind of double feedback loop, and when we think about it in terms of kind of ecological territory, what we really kind of dive into is these nodes or connections, and those kind of moments of feedback become connections between much larger systems. It gets to a place where we're beginning to understand kind of infrastructure not as these kind of single points, but this idea that we're embedding that infrastructure across larger territory. And that things like sensing and monitoring aren't really about a single phenomena we're trying to pick up, a single image, but that they begin to kind of correlate across species, across flora and fauna. And there's a couple ways kind of into that. And the ways I think that kind of changes in terms of our interaction with landscape is this concept, these kind of four concepts. One of them is this idea that we would be interacting with landscape through these, what I call micro-modifications. So with that, we're thinking about kind of changing these bottom-up processes, but modifying them through these kind of local alterations. So these become like resistances or shifts that we begin to change. The other one is this idea that I spoke about very quickly when I talked about the section on compress, but this idea of temporal exploitation. The idea that we're taking evolved systems, and we do this with many of the kind of things we construct in the landscape. We accidentally speed up or slow down very specific processes, and then we're going back and trying to remediate those processes, but that we can use those kind of, these ideas of temporal exploitation to our advantage. The other one here is this idea of novel relationships, and that we often shy away from this and move towards kind of known relationships, but this idea of building or creating these novel relationships actually is a way forward to imagine a new set of landscapes. And then the last one is this idea of phase manipulation, this idea that it's expressed through kind of small shifts rather than kind of changing a complete state, and that, in this case, like something like altering the water velocity or liquefying soil, those become ways of kind of changing the phase of a substance. And the last thing I'll say with that is that there's also this concept, and you'll see that in some of these projects, that what we're really working with is a series of protocols. We're kind of altering these kind of small protocols, and through those kind of smaller alterations, we're either speeding up or slowing down things, but what we're often doing is we're resisting the general tendency or the entropy of these landscape systems. So I know I have just a few more minutes, but I'm going to speak about just two projects here really quickly. I'll be upfront about both of them. That with what I've said before, the two projects are somewhat naive, but they get at the larger ideas that I've been trying to pick away at. The first one is a project that we did at Louisiana State University called PodMod, and we kind of had a team here, Charlie Pruitt and Brendan Deeden and Robert Herx worked on this. But what this project looked at is in the Atchafalaya Basin, ways of moving sediment or transporting sediment through the Atchafalaya River through a way of packaging that sediment, solidifying it and floating it, similar to the way we transport goods today. So just to give you a little bit of background on the Atchafalaya River, so if you're looking at this image on the left here, on the right, the white line kind of squiggling along is the Mississippi River. The Atchafalaya is this kind of shorter route out to the Gulf of Mexico. This is where the Mississippi River actually wants to go. But what you have along this whole area is you have a set of spaces where the water slows down, and when the water slows down, it basically drops all of the sediment out of it. And so when the water's moving at a higher rate, the sediment is carried or suspended in the water column, and we get to these areas where the water basically slows down and we lose sediment, and they're basically dredging it for navigation. If you look here, we basically have 70% of the water above this goes down the Mississippi, 30% down the Atchafalaya, but at that juncture where those two meet, we have a huge amount of the sediment from the Mississippi River actually moving down the Atchafalaya Basin, and that's basically just being captured within that basin, which is healthy, but it's an overload for the basin at this point. And then this is just showing kind of where those areas of low velocity are and how that water is slowing down. Particularly the idea that before we get out to the Gulf, we're actually dumping much of that sediment in spots. What the students did is they imagined all kinds of ways that this system might be altered. And what they came up with was this, as I mentioned, this idea of packaging the sediment and actually getting it past those low velocity points. And so a lot of their work and research went into how you might navigate past that system, but also how you might package and recycle that packaging once the sediment was pulled together. So that what they use is what's called the low sill structure. They imagine these inserts that would go into the low sill structure that would capture the sediment in certain spots. And funny enough, basically make these dirt sausages that would punch out the other side, be inflated on the top edge with this compostable material, and then be sent down the river like these pills or drones. You can laugh out loud. The idea, though, is while kind of wildly unfeasible, there's a kind of interesting, I think, set of things the students touched upon with this project, and one of them is the idea that the tuning of this system actually happens through kind of each of these volleys. And so not only does the system not just dump all the sediment down the Atchafalaya whenever the gates are open, but it basically can be scheduled with a whole kind of range of other operations that are occurring. So that kind of finding a system that actually can take on navigation, that can take on other kind of species movement, but trying to piece those together is, for me, became a very kind of interesting way that they were thinking about that and kind of willing to overlook, this whether or not the package is 100% feasible. One of the things they did do, which I thought was interesting, was some research into this kind of corrosive, this highly corrosive set of fasteners that they were using. And this set of fasteners basically would corrode as it began to hit the brackish or salt water. So, and that saltwater line is the line that kind of dictates where land is building on the Gulf. And so rather than using any kind of real technology here, what's happening is as it hits that saltwater line, which is always fluctuating, it's then dropping these capsules down into the bottom. And because they're packaged, they begin to build this kind of reef system. They did some other work with this that also looked at about how many dump trucks of dredge they could put out in a single day. But so in the end, this becomes, if we're looking at kind of the isohaline here with the red line, it becomes kind of an interesting, in my mind, approach to packaging that sediment, but also deploying it and interacting just through this kind of simple analog material with where it's deposited on the edge of the Gulf. And the last one I'll talk about, and then I'll shut down here, is the project you saw earlier where the students were looking at how you might begin to build a set of sensors that looked at the decomposition of algae. In the Atchafalaya Basin, algae is a problem because as it decomposes, it robs the water of oxygen. And as it's robbing the water of oxygen, well, I'll say upstream first. The bigger problem upstream is that we have all of these fertilizers coming into the Mississippi River. All those fertilizers are then nitrogens making the algae grow. What these students were looking at is a way to harvest that algae right at the specific moment that it was beginning to die off, and then take in the gases from that algae. And so this process is basically called hypoxia. So what you have is this kind of excessive nutrient levels. You have the algae growth. It dies off and it begins to rob the water of oxygen. Their approach then was to package once again the ecological process or this biotic process in this kind of long series of tubes. And as the algae decomposed, it would basically build these skins that would begin to shade portions of the water and cool portions of the Atchafalaya. Also, all of those gases that were creating were robbing the water of oxygen would be sequestered then within this kind of larger skins. Ideally, then, each of these could be slowly released, or they could be picked up and harvested for the gases if that was useful. But once again, I think both of these projects, and I'd be glad to talk about more. I know I'm kind of running out of time here. Both of these projects pick up on this idea that these kind of interactions with landscape might be much more about kind of tuning a set of behaviors as opposed to setting forth with this kind of larger scale kind of construction of infrastructure. I'm end on this slide, but hopefully, and I know I went a little fast with some parts, hopefully that kind of pieces together kind of an idea about how these ideas about responsive technologies, and I'll be the first to put out there that in landscape, and I would say in architecture, I think our use of these responsive technologies hasn't necessarily, it's just the beginning, but trying to look at an approach centered around landscape that looks beyond, beyond just visualizing, beyond just building these kind of human to machine interactions, but that's looking at how those kind of interactions might begin to be embedded in the world around us. Leave it there, and I'm sure there's lots of questions. Thanks. Yeah. Oh, repeat the question. So, why do we care about sediment? That was the question, right? I mean, I think it's okay. I mean, for sediment's a big issue, and so I'm going to try to do it really quickly because it's actually a pretty big issue. And I'm also a huge dirt nerd, so maybe it matters more to me than anybody else. But something like the Mississippi River Delta, there's a whole slew of reasons why the Mississippi River Delta is dying off. One of the reasons the Mississippi River Delta is dying off is that the sediment has basically been contained in the river channel itself, and it's never breaking out of its banks and replenishing the bayous around it, right? And so the typical way those delta systems work is, the river's working its way down, and once it gets to kind of a certain length, it finds a new kind of shorter course, it breaks, and then it basically begins to fill the land here with that sediment, right? So it's filled land, filled land, filled land, and then then basically breaks and fills land in another area. So my interest is that set of processes about the way land is built. I mean, that's building over thousands of years, huge territories, you know, like continental-sized areas of land or regions of land. My take on that is that using the, and I think this could be with any system, using the kind of entropy of those systems, I believe there's particularly in the Mississippi River, but this happens in any kind of deltaic plain. I believe there's more intelligent ways to choreograph that process of sediment moving down the river. And by choreographing that, and some of the models that we're working on, we're attempting to build land more logically, and so that it's not just kind of dumping it all in one area, but that we could then calibrate that to very specific platforms for different ecologies, different platforms for settlement, et cetera. So my take on it is, while I'm not that far with it yet, where I'm saying by doing these actions we can make this land exactly this way, my belief is that it can be choreographed in ways that are more articulated than they are now. Right now we're just dumping that stuff out in places, or actually trying to get it away. And my take would be that we could do much more with it. And it's a set of processes also that I think, for me, goes beyond just sediment. But it's a lot of the kind of models we're working with are very much about altering water velocity, which is what we've been doing for many, many years. But instead of keeping water velocity constant, what my take would be is that by altering it in different ways, we can actually change the way that land grows or shrinks over time. So I mean, some of the, well, I'll say that, I mean, for what we're doing right now, I don't have extended funding. I have funding through the next year, but I'm actively looking, and Army Corps is one of the people I'm talking to. But when I was in Louisiana at the Coastal Sustainability Studio, there's a group called CPRA, which is the Coastal Protection and Restoration Authority, and through that group, we developed many of these kind of quick models that looked at different versions of those sediment gates. And that was all funded through them, and there was quite a bit of funding to build those models. And when I say quite a bit, I mean we had to make $800 models. I have the Ferrari version of the model now, and back then I had the I don't know, the less. But yes, so it's groups like Army Corps, the Coastal Protection and Restoration Authority, those guys who have some money to throw at it. But we're not getting the money that the engineers are getting to do the actual sediment diversion that goes into the Mississippi now. And this is a change in the thinking on the Mississippi River, for example, where in the past it was all about building the levees stronger and higher. They're now building there's funding for these 5 sediment diversions that are actually going to go in, but these are kind of single gates. They're going to just be these diversions. They open them at times of high water, close them, and in order to flood the bayous. So, but that's a change in the way they're managing the river. Yep. So I think regardless, it's always there's always a scale relationship between the two, right? And so like in the lab, for example, if I use sand and say a clay, those are scaled in a way that sand is actually behaving more like a large gravel and clay is behaving more like sand, right? So that's when we scale them in the lab to say 1 to 1,000 or 1 to 10,000, we get slightly different relationships. And actually, to be honest with you, the reason we use the plastic sediment is because we can get it with very exact specific gravities, and those correlate more than the size necessarily to the behavior of, say, gravel. So like by matching the scale of the specific gravity, we can get something that's more accurate somewhat. But the other thing I would say is that that correlation between the real world and the fake world of that model I was showing with the plastic sediment, I actually haven't done a lot of work in trying to correlate those two, right? So like the actual behavior of the way the sediment works in the real world and the way it works in this model, those have been less of a concern for me in that model, and it's been more about making this what I always just call it this other place, right? And so it's a landscape unto itself, and what I'm trying to do with that landscape is have this kind of ongoing dynamic model that's always running, that we can begin to develop ways of sensing it or ways of modifying it that we can then maybe begin to speculate on the way those would translate out into physical systems, right? Because I think it immediately changes our relationship when we start to make these kind of very small modifications and they're based on these sensors, and that we can, you know, if we have, say, 15 variables in the model where there's, you know, an infinite amount in the physical world, we can begin to, as designers, I think, make more kind of precise speculations on what these new or new landforms or whatever it is. But I mean, the question's a good one because that scale issue is one that we're always dealing with, and it's important to either like divorce yourself from it or know exactly where you're off. You know what I mean? Because it's exponentially off once you're off. What makes them float? So they actually made one and it floated. Obviously didn't send one down the river, but they had a like a cellulose wrapper that held air. And so in the top, basically, there was a cellulose wrapper. In the bottom, there was this mesh. And so they would fill it then with the sand and then inflate the top, and then it would basically just float with that top edge on top of the water, right? I wouldn't draw too much into exactly whether or not it works. I mean, I would say they got as far enough to make the single prototype and have it floating, you know what I mean, in the lake near LSU. But in terms of exactly how that all came together, they didn't do enough work to really make the materials work in like in a robust way. Really more to get the idea across that you might attach material behavior to kind of like the territorial behavior of the brackish saltwater freshwater line. That you might be able to float these in areas of like slow velocity, and that's what they tried to show, is that it could float in these areas of slow velocity without and stay afloat long enough that it could make it down the Atchafalaya River. That's the type of things they kind of worked on. Does that make sense? Yeah. Okay. And I guess I don't say that also so you can't criticize that, because I think it's an easily criticizable project and we should get into it, but the part that I'm trying to present that I think is the most interesting about it is those kind of relationships that they made. I probably wasn't very clear on this, but I think one of the things that I'm most interested in is that where things are leading me somewhat is that we can't really model the Mississippi River, right? And that like all of these kind of modes of simulation are interesting, and they give us kind of insights and views into how we might engineer some of these systems. But in many ways, I think what becomes the most interesting is coupling this kind of large-scale sensing we're doing in the landscape, along with these local ways of sensing in the landscape, and using those two types of vision to think more about how these devices behave, right? And they change, and then understand what's around it and change something else, and that process alone of it changing its environment and altering it is the process it uses to learn or model its environment, right? In a similar way, and we can anthropomorphize that in a similar way to the way we learn about the world around us, through seeing and sensing and touching and doing. In many ways, like building these systems that slowly modify the ecological system in a certain direction, but learn about it and learn about its alterations is the way most of the work that I'm presenting here at the end is going. The modeling work, I think, is really more about understanding kind of very small local conditions for landscape architects, and less about saying we'll ever be able to make a model of the Mississippi that takes on all of its kind of intricacies. It's a great point. So if you go a little farther in the history of that modeling process of the basin model, it goes into what are called the HEC-RAS, or the Hydrologic Engineering Center models, and those are all digital models. And so all of the kind of numerical modeling they did for that went into these digital models they made. And what that slowly kind of moved forward is a set of ideas that lead us to where we are now with understanding what went wrong with the basin model, or the levee model, right? So part of that's about field observation, but a lot of it has to do with the numerical models and the digital models that they've built. What's interesting about those digital models, though, is that they're somewhat hidden from us, right? And so like it's easy to draw these correlations back to the basin model. I mean, the one I'm making is a very simple one, saying the channel's the same. Look at a map. You know what I mean? They're both the same. But there's probably, I mean, there's a whole other set of kind of political correlations. There's a whole other set of kind of cultural correlations around that model and the river's construction over time that I think the digital models are actually almost hidden from our view, right? But I believe the same set of push and pull are happening. And then, it's a much longer talk, but there's certainly a relationship between these ongoing living models of these systems. So there's several of these digital models of the Mississippi River that are kind of ongoing and living with the Army Corps of Engineers. And those are now in a dialogue, at least, with the river to some degree, right? So as they make changes, they're making changes back to the model, and they're slightly more they can alter one another. But the problem with the digital models, there's certain components that are actually very difficult to like rework, and part of that is the way sediment transport works, and that one in those models is one that's like it's a constant. I'm not exactly sure what the effect that's having on the river, but those constants become things that in a way weigh down certain parts of these dynamic systems. Yeah, and went as far, and basically went as far as it could, right? And then but yeah, I think the fact that the concrete plates could never be changed, right? Without a huge reinvestment in that model. Yeah, it actually became the driving factor for the river. I mean, in a way, the engineers, they could have remodeled portions of that, but in some ways, they knew how it worked, and it was almost easier to, like, basically go out and build that levee system, right? Thank you very much.